before what we did is if we had a function, and I'm just going to write a function down here, y equals, and this is example number 4 out of your textbook. If I had a function y equals 2 x, all right, we graphed that yesterday, and it grows fast. It kind of looks like a right half of a parabola, sort of. Well, let's just sketch the graph a little bit. So, well, actually, instead of sketching it, let's just graph it. So if I come in here and I say 2 raised to the x, and we look at the graph of that, for all the positive values of x, it kind of looks like a parabola. It's not quite a parabola, but it kind of looks like one. For the values less than, I don't know, in this case I would say less than -2, it approaches 0. In other words, as we approach positive infinity in the x direction, our y value approaches positive infinity. But as we come down around through here, our y value approaches 0 as x approaches negative infinity. So then the question is, what happens to this thing when I do this? When I subtract 1 from the x? Well, it looks a little different. Before, if we subtracted 1 from the x, it was usually in a set of parentheses in some way or form, and that was kind of like a horizontal shift. So let's graph the second equation and see what difference it makes. So I'm going to come in here, and for my second equation, I'm going to say 2 to the x minus 1. And then I'm going to hit graph. Okay? And it looks like it does shift it over ever so slightly to the right. Now, I say shift, but what's the formal fancy math way of saying shift, left or right? Does anybody remember? It's a geometry term, or you use it in geometry more often than algebra. Translate, right? So it's translated to the right. Now remember, when we translate horizontally, it's the opposite direction of the sign. And what I mean by that is we're subtracting 1, and normally in the x direction, minus means that we would travel to the left, but in this case, we're going to travel to the right. Does that make sense? Let's do another example. So this one, and I'm just going to write this in, this translates to the right. Similar scenario, except now I'm going to say 2 to the negative x. And who wants to guess and see? Who wants to guess as to what happens here? It flips it. Does anybody know how it flips it?
Y-axis.
The y-axis. Now, normally, if we have a leading coefficient, a negative in front of the x value, it would flip it over the x-axis. But in this case, because it's to the power, it would flip it in the negative direction. So I'm going to clear this one out, and I'm going to put 2 raised to the negative x. And so now what it'll do is it'll actually invert it. Because the reason for that is that the y values are based upon, why didn't I graph it? Oh, there it is. It's just slow today. Now it's probably going to change the screen. Oh, okay, we're good. Because the positive x values now become negative x values. So what that means is that right here, you know, like 2 to the third would actually become 2 to the negative third. And if I were to plug in 2 to the negative half, that would become the negative of that, which would be the positive 2. And so that's why you get a graph that looks like this. Does that make sense? Okay. And you can tell by also looking at the grid here. If you look at the grid here, the table of values, notice that the values for the y's are flipped. Okay? You have a 2 here, you have a 2 here. Right? 2, 2, 1, 1, 1 half, so on and so forth. those are all flipped, and that's based on that negative sign. Okay? Any questions so far? Okay, good. So what that does is this is going to reflect, is the fancy geometry term, over the x-axis, or I'm sorry, the y-axis. Okay? Let's do one more example. Now if I say y is equal to 3 times 2 raised to the x. Now before I do anything, can somebody tell me what they think it's going to do? Raise your hand and I'll point to you. Or you can just blurt it out. What is that 3 doing? Huh? Making it bigger. But what's a little more formal way to say it? What she's saying is, whatever our original value for this would be, we're going to multiply it by 3, so it would be bigger. But actually, in some cases, it would make it smaller. Right? Like when we have negative x values, it becomes a fraction. And when you take a fraction, oh no, wait, I guess it is always bigger. Oh, learn something new every day. Let me think that through a little bit. So it is always bigger. But what's a little more formal way? What would that look like graphically? It's a transformation that we're used to, and it doesn't have to be perfect formal language. Try to be a little more somewhere in the middle. I'll give you a clue. What's this? Stretching it. So we would stretch it vertically. When we make the y values bigger, what happens is it looks like it's stretched. So we're going to just insert here 3 times 2 raised to the x. And we'll graph it. So in blue is our original function. And it'll take a second because the calculator has to think. And it just takes that blue line and just stretches it taller. Now truthfully, it doesn't look like that much of a difference, but we are only multiplying by 3. Now I have a question for you guys. How is this important in the real world? When will we use this in the real world? Anybody know? Well, we use it in science all the time, especially, in fact, if you were to ask Miss Jasper Stump if she could help you out with that, she would probably have lots of growth models that you could use. So I'll give you a couple of examples. One particular example that always comes to mind is the growth of bacteria. Bacteria are usually single cell or very few cell creatures. And how do single cell organisms reproduce? If it's a single cell, how does a cell reproduce? You guys are, I see some of you guys making the signal with your hands. The cell grows and gets larger and larger until it's big enough to split into 2 cells. So one cell becomes 2 cells. What happens to those 2 cells if they eat and they grow? They become 4 cells. And then what happens to those 4 cells? They become 8 and then 16, and it's a doubling effect. And if you look at our table of values right here, if I start with 1 cell, I'll end up with 2 cells. And then eventually the 2 cells become 4 cells, and then the 4 cells become 8 cells, and so on and so forth. Well, what would happen if I started with 3 cells? Well, those 3 cells would double. And then that becomes 6 cells, and then those 6 cells would double. And then those 12 cells would double. So in the real world, what we do is we can either work backwards and figure out how many cells we started with, or if we wanted to reach a certain population by a certain amount of time, we could figure out how many cells we would need how many we would need to start with. Does that make sense? And so by using a mathematical equation, we can model that behavior. And so, for example, I don't know if you guys do this in your biology labs. Do you guys take cotton swabs and swab like doorknobs? and put it in a petri dish and then see how many bacteria grow overnight? Yeah.
We did that in science, and we did it on instruments, and it's disgusting. Cleaning
Yeah.
instruments.
But somebody sat down and mathematically figured out how long you need to take those petri dishes and leave them in an incubator. Right? If you leave them in too long, it's not good. But if you don't leave them in long enough, there's nothing to see. In fact, a lot of times it's a petri dish and it looks like it's got like a gluey substance on it, and you just wipe the cotton swab on it, and that cotton swab may have 5, 10, 20, 30 cells on it, and then what it does is over time, it multiplies, right? Because that sticky stuff is actually food for the cells. So they eat the food, they like a dark, warm temperature, and then they double and double and double, okay? Any questions on this one? Okay, good.